students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 2, which is a solution thermodynamics. So in this lecture, we are going to discuss about various methods for evaluation of partial molar property. So there are mainly three methods for evaluation of partial molar property. One which is a analytical method, and second both are graphical method. So let's start with the analytical method. Analytical method is the volume of solution is known as a function of its composition. The partial molar volume of a particular component may be found by partial differentiation with respect to amount of that constituent. That can be given by Vi is equal to, or can say that Vi bar is equal to del Vt upon del Ni at constant temperature, pressure, and Ni is not equal to J. So partial molar property that can be given by analytically using this equation. We studied this equation and fundamental of this equation in various previous lectures. So this is how we can calculate the partial molar volume or any partial molar property. Now let's discuss about the second method, which is a graphical method. Let Vt is a total volume of solution containing fixed amount of one of the constituents. Let's say that that component as N1 is known for several value of amount of other component, which say N2. We may to plot total volume against N2. Then that can be given by this figure. The slope of tangent to a curve is a value of, so this slope is the value of del Vt upon del N2. The limitation of this method is that this method has limitation of not yielding value of directly. Also, it not advisable to use this method for determination of when N2 is large compared to N1. The method of tangent intercept is free from such limitation and is thereof preferred for determination of partial molar property only for the dilute solution. So let's suppose value of N2 is a very dilute in a component 1 and N2 is a very small compared to the N1, then we are going to use this method. So if we want to find out the partial molar volume, then if we are taking slope in this method for the graph of Vt versus N2 and taking slope at this point, if we let's suppose for this mole I want to find out the partial molar property or partial molar volume, then using this slope I can find del Vt upon del N2 at constant pressure, temperature, and N1. So this is how this method is used. Now let's discuss about the third method, which is known as a tangent intercept method. This is also one graphical method. This graphical method is widely used for the determination of partial property of both component in binary solution. The molar volume V is plot against mole fraction of one of the component, say X2, the mole fraction of component 2. To determine partial molar volume, draw the tangent to curve at desired mole fraction. The intercept at this tangent made with vertical axis X2 gives the value of component 2 or partial molar volume of component 2, and intercept of vertical axis X2 at 0, or can say that X1 is equal to 1 gives partial molar volume of component 1, which show in this figure. So if we are going to find out the partial molar volume at this mole fraction, then here value of X2 is equal to 1. So we will get the value of partial molar volume. If we are going to calculate this section, then we will get V2 bar, and this intersect at X2 is equal to 0. So if we are going to measure this line, then we will get value of V1 bar. So this is how we can find the partial molar volume for both components. In previous method, we are just plotting Vt versus N2 graph. So here we can only find value of a particular component 2 or partial molar property of component 2 when N2 is less than N1 or N2 is very in dilute amount. So here this limitation is that we are only used for the dilute solution. But if we want to find out for other component, then we are going for the tangent intercept method. From this method, we can find out partial molar volume for both components by if we are going to draw the tangent and expand the tangent with x2 is equal to 1 and x2 is equal to 0. Then at x2 is equal to 0, if we are going to measure this line, we will get the value of partial molar volume of component 1, and if we are going to measure value of this BD, we will get the value of partial molar uh, volume of component 2. So AC, line AC is equal to partial molar volume of component 1 and line BD that give partial molar volume of component 2. To make more clear about this topic, consider this line BD which made from line BE and line ED. So can say that using this line BD or which is equal to V2 bar, so can say that V2 bar partial molar property of component 2 is that can be given by line BD is equal to line BE plus line ED. So using trigonometry, we can find the value of line BE. Line BE that can be given by line PE multiplication of this PE and PE. So can say that V2 bar is equal to multiplication of BE value of BP, which is a slope of this triangle. So slope of this triangle that can be given by del V upon del x2. So let's here write del V upon del x2, which is value of BE, and multiplication with value of PE. So what is value of PE? From this graph can say that 1 minus x2, which becomes value of PE, because these both sections are same, this x2 to D and this point P to point E, both sections are same. So can say that value of PE is equal to 1 minus x1. So del V upon del x2 multiplied by 1 minus x2 plus value of ED, which is our volume, or can say that molar volume that can be given by V. So if we are going to rearrange this equation, then it becomes V2 bar is equal to V plus 1 minus x2 del V upon del x2. So this is becomes our equation number 1. Now similarly, if we are going to find for line AC, if we are going to find for this line AC which makes this type of triangle A, F and P. So if we are going to find out for the line AC which gives the partial molar volume of component 1, so that we can say that line AC that can be given by line FC minus line FA. So line FC minus FA, we will get the value of AC. So this is the total line FC is equal to FA plus AC. So can say that line AC is equal to FC minus FA. So what is value of FC? Value of FC that can be given by molar volume. So let's write V here minus value of FA. Using trigonometry can say that value of FA that can be given by multiplication of FT multiplied by PA. So what is value of FP? Value of FP, which is x2 multiplied by value of PA again is our tangent, value of this tangent, then that can be given by del V upon del x2. So can write that del V upon del x2 here. So we will get the value of V1 bar is equal to V minus x2 upon del V, where value of V2 bar that can be given by V plus 1 minus x2 del V upon del x2. So this is our equation number 1 and this is our equation number 2. So this is how we can find the partial molar property and partial molar volume. Now this value is comes from graphical representation. Now if we want to find out the value analytically, we have to prove that this both equation is true. But if we are going to rearrange this equation number, then we can say that V plus this 1 minus x2 which becomes x1, so can say that del V upon del x2. So this becomes our equation number 3. So now let's prove this equation number 2 and this equation number 3 by analytically. This equation number 2 and this equation number 3 is find using the graphical method. Now if we want to find out this method is true or not, then we have to prove this both equations using analytical value. So let's prove it. So to prove that equation, let's consider a binary system which partial molar volume of component 1 that represent by V1 bar and for component 2 that can be given by V2 bar, and mole fraction of component 1 that can be given by x1 and mole fraction of component 2 that can be given by x2. Now molar volume can be defined as a V is equal to molar volume of component that can be given by V is equal to x1 V1 bar plus x2 V2 bar. Since binary system, we know that x1 plus x2 is equal to 1. So that can say that x2 is equal to 1 minus x1. So can write x2 is equal to 1 minus x1 using value of x1 in equation number, let's suppose this is our equation number 4. So using value of x1, let's taking this x1 is equal to x1 minus x2. So using value of this x1 in this equation number 4, then this equation becomes V is equal to 1 minus x2, replacing this x1 with 1 minus x2 V1 bar plus x2 into V2 bar. Now again simplifying above equation, we will get V1 bar minus V1 bar into x2 plus x2 into V2 bar. Taking x2 common from this both term, we will get V is equal to V1 bar plus in the bracket V2 bar minus V1 bar into x2. This becomes our equation number 5. Now differentiate this equation number 5 with x2. We will get del V upon del x2 is equal to V2 bar minus V1 bar del x2 upon del x2, which becomes 1 plus x2 as it is, and differentiation of V1 bar minus V2 bar upon del x2, which becomes 0. So can say that del V upon del x2, because differentiation of constant becomes 0. So this term becomes 0. So can say that del V upon del x2 is equal to V2 bar minus V1 bar. Here we are applying multiplication rule. If we are going to differentiate this equation with respect to x2, then it becomes del V upon del x2. Then this becomes 0 because differentiation of constant becomes 0. Then here we are going to apply multiplication rule. So first term will be constant and differentiation of this, then plus this term will be constant and differentiation of this. So if we are applying multiplication rule, that equation become like this: this becomes 0 due to this term is a constant. So can say that del V upon del x2 is equal to V2 bar minus V1 bar, which becomes our equation number 6. Using equation number 6 in equation number 5. So using value of equation 6 in 5, if what is equation 5? Equation 5, which is V2 minus V1 bar, V1 bar plus V2 minus V1 bar into x2. So this value V2 minus V1 bar replaced by this value. So can say that this V is equal to V1 bar plus V2 bar minus V1 bar. This V2 bar minus V1 bar replaced by del V upon x2. So it becomes del V upon x2 into x2. So here we can write x2. So rearranging this equation, we will get V is equal to V1 bar plus x2 into del V upon del x2. Again rearranging these equations by subjecting V1 bar, that can be given by V minus x2 del V upon del x2. So hence proven that this V1 bar value of this equation number 7 is the same as given by graphical method V1 bar. So equation number 2 and equation number 7 both are same. Similarly, we can prove for this V2 bar. So this is how we can use analytical method to prove this V1 bar and V2 bar. So this is all about today's lecture. I am going to complete my lecture here. Thank you.